All right, moving on to section 6.5, graphing trig functions. The second part here. So we spent time looking at our unit circle here in the first part of 6.5 and evaluating our trig functions with respect to the unit circle and their points. Sine being the y-coordinate, cosine being the x-coordinate, tangent y over x, and of course the reciprocal functions, cosecant, secant, cotangent. We're going to continue on with our topic of the circular functions, and we're going to use what we learned with the unit circle to help us build the models for our basic trig functions, our parent functions, our graph of y equals sine x, the graph of y equals cosine x, the graph of y equals tan x, secant, cotangent. So I'm going to build these parent models, and then we'll look at transforming those. So again, how do we transform these graphs? How do we shift them? How do we reflect them? How do we stretch or shrink the graphs, and how do they affect the key characteristics? So the first function we want to start off with, let's go to the graph of the sine function. So looking at the graph of y equals sine x. So remember, with the sine function, all right, y equal sine x, as we build this, just remember the sine, right, of any angle, right, theta, would equal the y-coordinate, right, with the unit circle. So if we're using the unit circle, we just need the y-coordinate. So again, if, for example, you want the sine of pi over 6, right, we know the sine of pi over 6 is equal to 1/2. We know the sine of pi over 4 is square root of 2 over 2. We know the sine of pi over 3 is square root of 3 over 2. We know the sine of pi over 2 is 1. So again, we can build a table of values. The sine of 3 pi over 4, right, is equal to square root of 2 over 2. And we can go clockwise, counterclockwise. We can do the negatives, right? We could go negative pi over 6, just sine value be negative 1/2. We can go negative pi over 4, just negative square root of 2 over 2. So again, you understand how to find some points. So again, just to write down a couple of these. Sine of pi over 3 is equal to the square root of 3 over 2. Right? It's equal to the y-coordinate. So that implies we have an ordered pair of pi over 3, square root of 3 over 2 on this graph. There's our ordered pair x, y that we can go graph and plot. So just like the sine of pi over 4, we know the sine of pi over 4 is equal to square root of 2 over 2. So that implies we could plot the ordered pair pi over 4, square root of 2 over 2. Right? So again, we can go through with all of these. And that's what I've done here on the next table. So here's our table of values. So I've got my input, my radian measure, and I've got their output. So sine of pi over 6, again, there's 1/2. Sine of pi over 4, again, this is square root of 2 over 2. Sine of pi over 3, this is equal to the square root of 3 over 2. All right, we know the sine of pi over 2 is equal to 1. So these are ordered pairs, right, that we can plot on our graph. Again, here's negative 1/2. Here's negative square root of 2 over 2 with the sine of negative pi over 4. Here's the sine of negative pi over 3, which is negative square root of 3 over 2. All right, so you could keep going and plotting these points. So I'm going to use that. So we're just going to build a graph. We've got some ordered pairs now that we could plot. So let's take those points, right, and let's look at those points here. So on this graph, example, sine of 0 is 0. Here's the point right here at sine of pi over 2. Here's that point, pi over 2, 1. Right, here's our point right here. If you're looking at pi over 4, this is the ordered pair of pi over 4, square root of 2 over 2. Right, and you got here, if you look at the sine of 3 pi over 4, and 3 pi over 4, we got square root of 2 over 2. So again, you're looking at these ordered pairs here. And here's pi, right? We know sine of pi is 0. And so forth. So we can keep looking at, right, these different ordered pairs that we've plotted here. And I've done that, both on the positive and the negative side of the x-axis. So again, building these ordered pairs, right, from the graph of the sine function. So again, using the unit circle, right, allows you to build a quick sketch of what this graph looks like. And you see as we produce the sine wave, right, as we produce this graph, right, we're looking at a wave that's continuous. It's no undefined values. No matter what you plug into S being the input variable here, the angle measure, we're going to get an output. And we're going to get an output between -1 and 1, which talks about our range. So looking at characteristics, we talk about domain of the sine function. Domain is all real numbers, -infinity to infinity. And our range, our graph takes place on the y-axis. Remember, domain is x, range is y. Our range is all y values greater than or equal -1 and less than or equal to +1. All right, and as we look at other characteristics from this graph, we talk about repeating pattern. We'll talk about the period. All right, the period is the repeating, all right, pattern. How often it repeats this wave. And you can see this wave here, and I'll look at it. For example, if you go from -2 pi all the way to 0, right, that's the same as we have from 0 all the way to 2 pi. So every 2 pi, this sine wave repeats. So again, it's the same wave, and you got your max and min points at all these y-intercept points on the unit circle, your pi/2 marks, right, pi/2, -pi/2, 3pi/2, -3pi/2. So you see where the intercepts take place. And you can also see that your zeros, your x-intercepts of the graph, right, take place at all the multiples of pi, right? Any multiple pi, we're sitting on the x-axis. We're sitting on a y-intercept point, all right? And how about taking that a little bit further? Let's break that down. And we talk about the zeros and x-intercepts. I'll write that down in here. Erase that. All right, so our zeros, all right, and remember our zeros are our x-intercepts, right, locations. So where our graph crosses the x-axis, where the function equals zeros. Again, located at all multiples of pi. Any multiple pi, right? We're sitting on the x-axis. Sine of pi 0, sine of 2 pi 0, sine of -2 pi 0, sine of -pi is 0. All multiples of pi, we're sitting on the x-axis. Location of the x-intercept points. All right, and again, our max values. Let's talk about the max points. So we look at some other characteristics. So our relative max points are located at what? Pi/2. All right, and all coterminal. All angles coterminal with pi/2. Now remember, how do we find coterminal angles? We add or subtract any multiple of 2 pi, right? We subtract on the angle coterminal with it. So pi/2, -3pi/2, which is pi/2 minus 2 pi. Right? We could go over to pi/2 plus 2 pi, which would be 5pi/2. We'd have another max point. Those are your max points. Now your min points. You can see these relative mins where our graph changes from what? Decreasing to increasing. They're located at 3pi/2. Right? And all coterminal. angles. So all angles coterminal with 3 pi over 2. So again, add, subtracting, and multiple 2 pi. All right, we'll be back. All right, looking at another min point, and our min points, of course, max value is 1, min value is -1. Right. So keep that in mind. What is our max value? What's our min value? Right. So 1 and -1. We also have symmetry. You talk about symmetry with this graph of the sine function. This graph is symmetric with respect to the origin. All right. Now, when you say a graph symmetric to the origin, that implies we got what we call a odd function. Even function, graph symmetric to the y-axis. Odd function, graph symmetric to the origin. All right, so with that said, that means this odd function, you remember back to origin in our algebra course, we know that f of -x equals negative f of x. So that implies the sine of -x equals negative sine x. All right, so again, that's with odd functions. That's true. So a little review there on that. But those are key characteristics. We want to talk about another one, and that is the height, what we call the amplitude. All right, amplitude is the height of your wave. All right, and the amplitude, if you look at your max and min points, they occur at 1 and -1. So the amplitude is always calculated as 1/2 the max minus the min. All right, so the amplitude is 1. All right. So again, if you want to look at a formula, amplitude equals 1/2 the max minus the min. So that equals what? 1/2 of the max, which is 1, and the min, which is -1. And we simplify that down, that's 1/2 of 2, which is 1. Yeah, so our height, we're going up 1, we're going down 1. So we have an amplitude of 1. So again, that's from your resting position. The resting position is the x-axis. This wave oscillates between 1 and -1. The height of that wave is 1. So again, 1/2 the max minus the min would always calculate your amplitude of any wave, right? This sine wave, for example. So just to summarize these characteristics, you can see again on this page here, looking at those things we've mentioned on here. And again, with it being a periodic function, we know that repeats every 2 pi. So we can come up with that conclusion. The sine of s plus 2 pi is the same as the sine of s. So you start talking about shifting graphs. If you shift a graph to the left 2 pi, you're going to get the same function back, and that'd be left or right. You do plus or minus 2 pi. Be right back on the graph because again it repeats every 2 pi. So if you were to translate or shift that graph. All right, and again mentioning amplitude, you can see again the calculation of that here on the next page, and just showing you those key characteristics. Now you also have your calculator. So anytime you want to build your parent model to look at this graph, let's go to our TI. So let's pull it up. So going to y equal to, let's type in the sine of x. And if we're to graph this, I'm going to go to the zoom button. You see in your zoom at the top is zoom. Go in there and you'll see command 7. Command 7 says zoom trig on your calculator. Let's hit that command. And that builds what we call a trig window. Now a trig window is scaling out your x-axis from -2 pi to 2 pi. All right. So I want to show you that real quick. Let's write on this graph. All right. So if you look on this graph here, we're going to scale from, again, -2 pi. So our min over here at -2 pi and our max over here at 2 pi. And every pi over 2, right, you'll see your graph scaled out on your TI. You'll see it marked. Every increment of pi over 2, every 1.57 units on the x-axis. Remember, pi divided by 2 is 3.14 divided by 2. So again, as you're looking at this graph, right, and it gives you some good points to look at visually on this window. We know our pi and pi over 2 marks are intercept points from our unit circle. This is when sign is equal to 0 or 1 or negative 1. So you see those ordered pairs, just like this point here. That's the point pi over 2, 1, right? The sine of x. So here's our graph of the sine function. And you can see the zeros at pi, negative pi, 2 pi, negative 2 pi. All right, so I just want to show you that on there. So that's your graph of that function, just building a quick window of that. All right, let's go to your table. If you look at your table, second graph button, and you can see in here those ordered pairs. Sine of 0, 0, 0, 0 is on there. And you can see in here, if you look at different measurements, you can see your ordered pairs. Again, domain all real numbers. You get an output for each, no matter where you're looking on that graph. But again, that's the graph there along the trig window. So doing the trig window, just make sure your mode, we're in radian mode right now. So make sure we're in radian mode when I'm doing this trig window. It's going from negative, and hit your window button. It's going from around negative 6.28. It should be a minus, a little off, but negative 2 pi to 2 pi to 6.28. And it'll scale it out every 1.57 units on the X scale if you're using, again, the trig window. And you can always manually change it. I could put in here negative 2 pi, right? I could put in 2 pi for the X max if you wanted to build the trig window. And again, the scale here, pi over 2. That will be your scaling it out on the x-axis. So again, you can build that in there and see the graph. So I just want to show you got your calculator. So I'll give you again a quick picture. See your domain of all real numbers, your range between negative 1 and 1. Again, where it takes place in the y-axis, continuous, repeating every 2 pi. All right. So moving on, let's move on to the graph of the cosine function. So we've talked about the sine function, and we've analyzed it, and we've looked at it here, so different characteristics on our calculator. Now, on the cosine model, we're going to do the same thing. Let's break out our unit circle again. So again, using the unit circle, and we can write our definition back up here. We know y equal cosine x. Well, we know cosine is evaluated by the x coordinate on the unit circle. So all we got to do is find some points on the unit circle, like pi over 6, and our x coordinate, which is square root of 2, cosine of pi over 4, square root of 2, cosine of pi over 3, 1/2, right? So again, if I was asking you to find the cosine of pi over 3, that's equal to 1/2, right? The x coordinate. So that implies an ordered pair that we could go plot is pi over 3, 1/2. Could plot that point. Just like down here, we got negative pi over 6, negative pi over 4, negative pi over 3. Yeah, we know the cosine of negative pi over 6, for example, is equal to the square root of 3 over 2, right? There's the x coordinate, right, looking at that point. So we could go plot that ordered pair, negative pi over 6, square root of 2. So it gives us an ordered pair. And of course, at pi over 2 and negative pi over 2, our cosine value is 0. So we see our x coordinates are 0. We know the cosine of the multiples of pi, right? We get a x coordinate of 1 or negative 1. So this is where our max and mins are going to take place. So you're sort of switching it up from our sine wave. So building our table, I've done that here on the next page. So there's our table of values. So here are our x and y coordinates. We can plot these ordered pairs. So again, we know that 0, 1 is on there. And this is again the cosine of pi over 6, which is square root of 3 over 2. So again, we can plot that point, pi over 6, square root of 3 over 2, right? Get a graph of it. And here's our point. Again, this is square root of 2 over 2 is a decimal. Here's 1/2. So again, we plot that ordered pair. So you can build your table of values, right? And you go plot it. So again, finding some quick points, that's easy to do with the unit circle. So taking those points, all right, let's go ahead and look at its graph. So here are those ordered pairs coming together and making this graph of the cosine function. So again, cosine of 0, which is 1, there's the point 0, 1. Right here, the middle mark, this is our pi over 4 mark, pi over 4 radians. Here's that point, pi over 4, square root of 2 over 2. Right, here's pi over 2, 0, one of the x-intercepts. Right, here we got the point pi negative 1. Right here at pi on the x-axis. Here's 3 pi over 4. So I'll plot that location. Again, this is a standard trig window as we're looking at these different ordered pairs. There's 3 pi over 4, negative square root of 2 over 2. Here's 3 pi over 2, 0. Right, and here's our point 2 pi 1. Right, over here is the point negative 2 pi 1. Well, looks some points on the left side of the x-axis. Here's negative 3 pi over 2, 0. One of the x-intercepts. Here's one of the min points. Cosine negative pi is negative 1. Here's another x-intercept point. Cosine negative pi over 2 is 0. So you see your graph. So just talking about the key characteristics. We know our domain, like our sine wave, is all real numbers. We know our range, just like the sine wave. The graph takes place between negative 1 and 1. Those are our max and min values on the y-axis. So that's our range. We know the period, the repeating pattern for this graph. The period, just like the sine wave, is every 2 pi. You can see on this graph, as you look from negative 2 pi to 0, for example, that's the same exact graph as we get from 0 to 2 pi, right? It's repeating, it's oscillating every 2 pi, getting the same wave back. We also know the amplitude. We know the height. We calculate the amplitude of this function. What's the height of this wave? Just like the sine wave, our max and min points are at 1, negative 1. So our amplitude is equal to 1. Again, amplitude, remember, equals 1/2 the max minus the min. So again, 1/2 of 1 minus negative 1, which is 1/2 of 2, which equals 1. So that's amplitude. Now, as far as symmetry goes, we talked about symmetry with the last one. This graph is symmetric with respect to the y-axis, right? The y-axis spits this graph right down the middle. All right, so let's go ahead and write that down. And if you remember, what type of graph we have symmetric with respect to the y-axis with functions is an even function. So yeah, this is a even function. So that implies even function. Now with an even function, all right, our function characteristics, f of negative x equal f of x. So that implies the cosine of negative x will equal the cosine of x, right, based off it being a even function. Talking about the zeros, let's go ahead and put in those characteristics. So the zeros, again, different from our sine wave, where all multiples of pi were our zeros. Now all multiples of pi locate our max and min points. Our zeros are located at what? Pi over 2 plus or minus all multiples of pi. So let's go ahead and write that down here. So our zeros, right, or our x-intercept points, right, we have located at pi over 2, all right, plus or minus all multiples of pi. So yeah, pi over 2, we add pi, right? We're going to look back at 3 pi over 2. If we subtract pi, we're going to be at negative pi over 2. All right, subtract another pi, we get negative 3 pi over 2. So again, all multiples of pi. All right, we're going to look at, again, our x-intercepts, our zeros. Now, as we look at our max and min points, the max and mins, well, let's talk about the max points, right, where we see our max value of 1 on this graph. We notice, again, those are located at 0, right? Located at 0 plus or minus all multiples of 2 pi. So I'm going to write that down. Located at 0 plus or minus all multiples of 2 pi. So, again, what's that mean? Coterminal. Coterminal with 0. All right, and then our min points. Locate those where we see our min value of negative 1. Well, our min points are located at pi plus the multiples of 2 pi, coterminal angles. All right, located at pi plus or minus all multiples of 2 pi. So again, the coterminal angles. All right. So again, that's some key characteristics. So with these, again, we want to know these key characteristics as we're looking at our sine wave, our cosine wave. All right. And again, you can build that graph if you want to look at it on your TI. You can put it in there and take a look at it. But here, all those characteristics summarized for you. Next few slides, just breaking down these characteristics we've gone over. And again, there's those table of values that we use, and we use the unit circle to produce those points. All right, with that said. And if you want to look at similarities, summing up the two, we've talked about domain and range being the same, the period being the same, the amplitude being the same. Only thing different is with symmetry, we have one being symmetric to the origin, we have an odd function with sine, we have an even function with cosine. Again, on your TI, I'm going to go back to it. Since we still have the sine wave in there, we can even look at the cosine wave. We can put it here in Y2 and graph them together. So you can see the two graphs here together, which the graph here in black is my cosine wave with the y-axis splitting it right down the middle. Right? And again, if you look at that graph, right, that's a graph shifted. So the cosine wave graph is a graph of the sine shifted left pi over 2. You shifted left pi over 2 radians, the sine wave, the graph in blue, right, you get that same graph back. So again, there is some transformations. I'll write that on here. Good thing to look at. Let's pull that up so we can analyze this a little further. All right. The sine of x plus pi over 2 equals your cosine function. So again, you take this graph example, this point here. Right? You shift it left. You subtract pi over 2. Right? That's what this is here. This is x minus negative pi over 2. Shift left pi over 2, 1.57 radians. So you can see that transformation. So you can take every point and shift it left pi over 2. And you get your graph back. So again, building your graph of your cosine function, right? You can use your sine function to do that. So you can see that here with the sine wave. So you can see all those points from the sine wave shifted left pi over 2. Okay? So transformations, we can use those to help us. If we can get a visual of the very basic parent model, we can go from there to build our different graphs. No matter what kind of function we start to look at, as we build on it a little bit more later on in this chapter. We'll look at some more transformations. All right, so let's go ahead and finish off the sine and cosine with an example. So I want to take a look here at the first example. It says make a hand-drawn graph. Sketch a graph of y equal cosine x. All right, let's go ahead and do that. Let's go ahead and build it. So the first thing I want to do, if I'm building the y equal cosine x graph, Let's go ahead and build in the x and the y-axis. And let's build it based off a trig window. This is going to be true with any of my graphs. So let's scale it out. Every pi over 2, we'll mark it. And we know it repeats every 2 pi. That's the repeating pattern. So I'm going to go to negative 2 pi. I'm going to also go to positive 2 pi. Of course, we know it repeats. After that, same characteristics every 2 pi. And of course, here's 0. They're in the middle. And I'm going to mark the y-axis. Up 1, down negative 1. It's our range, remember, between 1 and negative 1. So as I'm sketching in, let's go ahead and sketch in the graph. So doing part A, I want to graph y equal cosine of x. Well, with graph y equal cosine of x, just remember, cosine of theta equals the x coordinate. So if you're building it from scratch again, you can use these examples. So that implies, for example, what's the cosine of 0? The cosine of 0 is what? 1, right? We know on the unit circle that we have an ordered pair of 1, 0 at 0. So cosine of 0 is 1. So I can plot that point. So that implies the point 0, 1 is on the graph of the cosine wave. All right. We also know if we're looking at the cosine of pi over 2, cosine of pi over 2 is 0. So I can plot that point, pi over 2, 0. Right? So pi over 2, 0 is on the graph of the cosine function. We know at pi, for example, we know the cosine of pi is equal to negative 1. The ordered pair is negative 1, 0 at pi. And you can get your unit circle out if you need to look back at it to see those points. So just remember, you have the unit circle to help you if you need it. So pi negative 1 is another point that we can plot on this graph. I know the cosine of 3 pi over 2 is 0, so I'm going to go ahead and plot that point. I know the cosine of 2 pi is 1. I know the cosine of 2 pi is 1. So here, between 0 and 2 pi, right, I can go ahead and sketch in this way. And we know this graph repeats itself. So I already know what the left side looks. I'm going to go ahead and finish it out. So here's our graph of cosine x. So we want to fill in these other points. Yeah, negative pi over 2, 0 is on there. I know negative pi, negative 1 is on there. I know negative 3 pi over 2, 0 is on there. And I know negative 2 pi 1 is on there. But there's a graph of y equal cosine x. All right, well, let's go to example B. So in example B, right, it wants us to sketch in. It says, what's the graph of y equal to the cosine of negative x? Now here's where we got to review some of our transformation properties. All right, we know that a negative, anytime we multiply by a negative, that causes a reflection. Now if we multiply our domain variable by a negative, reviewing transformation properties, we're going to multiply all the x coordinates by negative. We're going to flip the y-axis. So that implies reflect the graph of y equal cosine x, which we already have sketched over here in black to the side. Reflect the graph of y equal cosine x across the y-axis. Right? Every ordered pair, so that implies every point xy, we're going to plot the point negative xy. So, for example, right here at pi negative 1, we reflect across the y-axis. We'll be over here at negative pi negative 1. Right? Pi over 2, 0. If we reflect across the y-axis, we'll be at negative pi over 2, 0. Right? 2 pi 1. If we reflect directly across the y-axis, we'll be at negative 2 pi 1. So again, I'm reflecting the y-axis. Well, if we do that, we get this same exact graph, and highlight it here in red. we reflect the graph of your cosine function across the y-axis. All right, we get the same graph back. All right, that implies same graph as y equal cosine x. Yeah, that implies cosine of negative x equal cosine x. And that's true, because remember, we have a even function. This graph is symmetric to the y-axis. Symmetric to the y-axis means we reflect the y-axis. Nothing different is produced from that graph. So you can see the graph is the same. So if you look at part D, it says how the graphs in part A and B compare. They're the same. All right. Now let's look at another reflection. So say we reflect not the y-axis. Let's look at reflection across the x-axis. Let's turn this graph upside down. So if you look at part C, it wants us to graph in y equal negative cosine x. So the negative's out here in front. So that implies reflect, right, the graph, right, of y equal cosine x, right, across the x-axis. Turn it upside down. So that means every ordered pair, x, y, will give us the ordered pair of x, negative y. So if you look at, for example, 0, 1, we reflect across the x-axis. We're going through the point 0, negative 1. Right, pi over 2, 0, still pi over 2, 0. But pi, negative 1, we reflect across the x-axis. We'll be over here at the point pi 1. So you see that mirror image across the x. 3 pi over 2, 0, still 3 pi over 2, 0. 2 pi 1, we reflect across the x-axis. We're going to be at 2 pi, what, negative 1. So every ordered pair on the graph cosine x, we're going to flip directly across the x-axis. And that builds our new graph, right? So we're using transformations to easily sketch this graph. So as we sketch in the graph of this cosine function, this is the cosine function, flipped across the x-axis, turned upside down, here in blue. Here's our graph. Of course, it goes on forever. These graphs don't stop, right? They keep moving. They keep going on there forever. But you see your graph reflected across the x-axis. So again, repeating every 2 pi, so we know these graphs, right, continue this pattern. Right? But there it is in building our model. So again, using the unit circle. So remember, you've got your unit circle to help you in building these graphs. Use those points from the unit circle to help get those. Right? Same thing happens, right, if you do the sine wave. So if you were to build the sine function, so let's go ahead and finish off this set. Let's look at the sine wave. So I'm going to go ahead and build in my xy axis. All right, I'm going to go ahead and scale it out. So here's 0 radians every pi over 2. Negative pi over 2. Negative pi. Negative 3 pi over 2. Negative 2 pi. Pi over 2. Pi. 3 pi over 2. 2 pi. Scale it out on the x-axis. Increment every 1.57 radians. And then we got our max. And we got our min at 1, negative 1. So graphing in. So as we start out with the sketch, y equal to the sine of x. So remember the sine of theta. The sine of theta is equal to the y coordinate. So again, use your unit circle to help you find some points. So that implies, for example, the sine of 0. What's the y coordinate of 0? The y coordinate of 0 is 0. So that implies 0, 0 is a point we can go plot. We know the sine of pi over 2. Sine of pi over 2, the y coordinate is 1 at pi over 2 on the unit circle. So we got an ordered pair of pi over 2, 1 that we can go plot. So plotting these points, we know it passes through 0, 0. So I'll go ahead and plot 0, 0. Know it passes through pi over 2, 1. Sine of pi over 2 is 1. We know the sine of pi is 0, so it passes through the point pi 0. Sine of 3 pi over 2, y coordinate 3 pi over 2 on the unit circle. is -1. Sine of 2 pi is 0. So between 0 and 2 pi, let's go ahead and sketch in what we found. Let's go ahead and build that in. All right. So looking at our graph. So there it is. We've gone from 0 to 2 pi, right? Now the same thing happens on the left side. So if you're looking at sine negative pi over 2, that's -1. The sine of negative pi is 0. The sine of 3 pi over 2 is 1. The sine of negative 2 pi is 0. So forth. So you can plot these points too. -3 pi over 2, 1 on our graph. We know again sine negative pi over 2 is -1. So negative pi over 2, -1 is on the graph. We know the negative pi 0 on there. But there are points, just looking at these ordered pairs. Right? Building a graph of our sine function. So there's y equals sine x. Right? Now moving on, let's go to our next one. Let's go to the graph of sine of x minus pi. All right, so if you want, we can put this one in red. What's the graph of y equals sine of x minus pi? Now, the sine of x minus pi, that implies we have a horizontal shift. Right? This implies we need to shift, right, the graph of y equals sine x, which we already have graphed here in black, right, to the right. Pi radians, pi units, right? 3.14 units. So that implies every ordered pair on the graph of sine x, we're going to be looking at x plus pi. Why? We got to shift it to the right, so we subtract pi from it. So as we do that, let's go ahead and shift this graph. So, for example, we got pi over 2, 1, right? We shift that to the right. What's pi over 2 plus pi? That's 3 pi over 2. So if you go to the right, pi, we're going to be right here. We're going to be at this point, 3 pi over 2, 1. We've added pi to that, shifted to the right. So it passed through the point, 3 pi over 2, 1. Now 0, 0, we go to the right, pi, we'll be at pi 0, right? We know the ordered pair. Let's take the point negative pi over 2, -1. If we add pi to that, we're going to be right here at the point pi over 2, -1. Right? We know that negative pi over 2 plus pi, right, we get to pi to 2. So there's that point that we can use to plot. It's like -3 pi over 2 of 1. If we add pi over 2 to that, we get pi over 2. So we can go ahead and plot that point. We know pi over 2, 1 will be on this graph. All right, we know -2 pi shift to the right, going through negative pi 0, adding pi, remember, to every x coordinate. All right, looking at these points as we're building in this graph. So with that said, I've got enough to sketch it. So if you look at this graph, and we built it in here, all right, we can go ahead and connect these. So looking at our graph here in red, so graph shifted. Right. Pi. So there's our graph, and this continues. That pattern repeats every what? 2 pi. Well, there's the graph of y equal to what? The sine of x minus pi. You put in your calculator if you want to check it to look at that. Well, there's its sketch. So it's using my parent model to quickly sketch with transformations. If you look at example C, it wants you to sketch the graph of y equal to negative sine x. Well, that says what? We need to reflect, right, the x-axis, multiplying by negative. So we're going to take our sine function and reflect the next axis. So if we take pi over 2, 1, we'll be over here at pi over 2, -1. Right? If we take -3 pi over 2, -1, we'll be up here at the point 3 pi over 2, 1. 0, 0 will stay 0, 0. All right, negative pi over 2, 1. Moves up here to pi over 2, 1. And it's still here at 0. We got negative 3 pi over 2, 1. Flip across the x-axis. Be down here at negative 3 pi over 2, negative 1. So you look, I'm graphing here in blue, what's happening? I'm getting the same exact graph I got with the sine of x minus pi. All right? So that implies same graph as y equal to the sine of x minus pi. All right? So if you look at part D, how the graphs in part B and C compare. They're the same graphs. All right? So yeah, the sine of x minus pi, and we can write that in here now. Sine of x minus pi equals the sine of x in our graph. So that's a summary of our sine and cosine functions. Just giving you an in-depth look at those, their characteristics, domain all real numbers, range -1 to 1, period 2 pi, amplitude of 1. Those are our key characteristics of our parent models, sine and cosine. All right, we'll stop there, and then we'll continue on looking at the tangent function and then the reciprocal models if we move on in this section.